There we go. So I'll pray. Dear Heavenly Father, we thank you for this day. I thank you for these students and for everybody waking up this morning to come to class. And just pray you guide our steps today. Help us to understand what we need to about factoring in the time that we have, Lord. In your name I pray. Amen. So let me get straight into an example here. So example 1. So this is a kind of problem that I missed. Well, I mean, not missed, I just didn't get to it last time, right? 7x to the 5th plus 14 minus ax to the 5th minus 2a. And so we're asked to factor this guy here. All right? What do you think we should do with this one? Any ideas?
Put
Yeah.
it in parentheses and then combine my terms.
You guys are saying the same thing. So yes, factoring by grouping is when we put things in parentheses. So here we can factor 7 out, right? And we have 7 and an x to the 5th plus what? Plus 2, right? And here we have an a, right? So I can factor out actually a minus a. And again, I have an x to the 5th plus 2, right? So factoring by grouping is when you look for a common thing amongst two pairs, let's say, and like factor that same thing out. Once you have that pattern, then you can factor the x to the 5th plus 2 out of both of these, which gives you what? So this 7 minus a times x to the 5th plus 2. And that will be the answer here. Now, I mean, it is true, if you're a math major, a good math major, you could factor that further. But it's not easy, all right? And it's certainly not something I would expect you guys to do, right? And this is what the book expects for the answer of this kind of problem, yeah. Any questions about anything else before I go on to the next example? If you're still having trouble getting into my labs or something, just email me. I have by now as I've listened to all of the different students tell me what their problems were and how they got into it, I kind of have a list of steps to go through at this point, which I just emailed somebody who asked me about it. So if you're such a person, email me, and I will email you the list of steps. Okay, so another one of these. Well, actually, not another one of these, a different one altogether. How about this one? 6x squared. Oh no, I think I did this one last time. Let me not do that one. My bad. Sorry, guys. So here's another one. 5x squared plus 14x plus 8. All right. Can we factor this? Yep.
Wouldn't you multiply 5 times 8 and then see what number you multiply? It would have to add up to be 14, correct?
Uh-huh.
So you multiply 5 times 8.
5 times 8, yeah.
And see which two numbers out of the 40
Mm-hmm.
add up to 14. And then you would take those two numbers and put them in place of the 14 and then factor.
Something like that. Let's see here. How about if we put a 5x? I mean, what you're remembering is like you wrote a table or something, maybe. Different algebra classes teach people about 6 different ways to do this, all right? My way is very low tech. It's just guess and check. So I guess a way to split this, right? So 5x squared, I can either split as 5x times x, or, I mean, if you wanted to be really silly about it, you could do this. But this like never happens in any of the problems you guys are assigned pretty much. But I mean, technically this times this is 5x squared too, right? But we start with whole number ways to factor 5, right? So it's just 1 times 5, or of course minus 1 times minus 5, but that's really not any different for us here. So I'm pretty much forced to write down 5x and x here as my starting point. And then, like you said, the question is, how do we get that 14x, right? Now, whatever number I put here and here, it has to multiply to give 8, right? How can we get 8? We can get 8 from 1 times 8 or 2 times 4 or minuses times minuses. I don't think we need minuses. Everything's plus. So let's try 2 and 4. See what happens, right? Let me try 1 and 8 to show you what it... Let's try 1 and 8 because it won't work. I'm making it not work on purpose, okay? X plus what? 5 times 8 is 40. So this would be 41x. So this is not right, right? So I guessed something. I checked it. It didn't work. So what do? I go, nope, that's not it. Then I try the next choice, which would be 2 times 4, like we were saying. Does 2 and 4 work here? Yeah, it still fails. Like you were saying, I have to switch it because that gives me 2x plus 20, which is 22. Still, we check, it doesn't work, right? But you thought we just need to flip those, and then we'll get that 14 that, what was your name? Gabrielle was talking about, right? That 14 is what we need to get. So this gives us 10 plus 4x, which is 14. All right. So listen, whatever method you've been taught before, the ultimate question is, after you've done your method and you've come up with the factoring, does it work, right? So we should always check, multiply it out. You get back where you started. If you did, great. If you didn't, try again, right?
Can't you also just like multiply like 8 times 5 and then try to get like find an answer between one of those numbers to get like...
Okay, so let me write down the steps. Multiply 8 times 5, you get 40. Then what do we do?
Then we try to find something, yeah.
So you try to find a and b such that a plus b equals to 14. Okay.
So it would be like...
This is such that. Yeah, what?
10 and 4, that would be 14.
So you guys,
Yeah, that's what I was...
you have this creative spark to say, aha, a equals, what'd you say? 10, b equals 4, and then what do we do with those?
And then you take in place of that, so you're going to rewrite the whole equation. So it's going to be 5x squared plus you're going to have 10x, and then those go in parentheses. And then
Parentheses where?
around the 5x squared plus the 10x.
Like that?
No, in front of the 5. Yeah. And then around the, after the x. And then it would be parentheses 4x plus 8. And then you would factor the 5x out, which is 8. X plus 2. And then the 4 would be factored out, which would be x plus 2. So then you would take 5x plus 4 and x plus 2.
Oh, wait a minute. So the thing that was lost in translation here is you said another parentheses, but what I didn't pick up on was you're saying add these two things. Because without addition, this doesn't make sense. I mean, it's not going to get us to the answer anyway, right? So this plus this, and then you're like this. There's a plus here, right? And then you're like factor by grouping. And that's the answer we got, right? Now, if this method works for you, great, use it. But this is not personally how I think. And so if you've been taught it before, this is like your home, your happy place, right? Great. If you haven't been taught it before, the rest of you are like, what are we doing? Which is fine. The point is, you have freedom here. You can do it like I'm doing it with which just guessing, or you can go through this method here if you want to. Other people have notation for this, like a grid, and they put numbers and things. But I mean, if you guys want me, I can show you an algorithm for factoring. Do you want to see something that always works? All right, watch this. So what's the difference between, my algorithm in here is somewhat ad hoc. I write down a template for what I'm looking for, and then I just plug numbers in, check it, and keep adjusting the numbers until it works. All right? I'm fairly certain that's almost the fastest way to do it. Now, so the algorithm is this. If you're given x squared plus, let's say, bx plus c. So let's suppose that we have a leading coefficient which is 1, just to make the discussion a little bit less complicated to start with here, okay? And we want to factor this, okay? So here's what we do. We notice that number 1, x squared plus bx plus c is x plus b over 2 quantity squared, right? Well, I mean, you say, what do you mean right? What are you talking about? Well, what happens if you FOIL this out? If you multiply that out, what do you get? You get back x squared plus b over 2x plus b over 2x plus b squared over 4. In other words, you get these two terms, but you also get an additional term of b squared over 4 when we multiply this out. So to be fair, I have to subtract a b squared over 4. Listen, I'm going to illustrate this with some numbers here in just a second. Let me just finish sketching the general algorithm for you guys, okay? So that right here, these guys are identically these first two terms. Now the plus c, it's still there, so we have to add it, okay? And then step 2 is there's two things. If c minus b squared over 4 is greater than or equal to 0, you're done. You're done, in the sense that either it's a prime polynomial or it's just a squared thing. The other case is if c minus b squared over 4 is less than 0, you can use difference of squares to factor it. Here, I'll show you an let me work through this on an explicit example here, okay? So like, I think I probably did this one last time, but I'll do it again here. So suppose you had x squared plus 4x plus 5. So what this algorithm says is it says you take half of the coefficient of the x term. What's half of the coefficient of the x term on my example? I've got 4, so half of 4 is 2. So this I rewrite as x plus 2 quantity squared. Now, I can't just do that. What have I done if I do that? I have added 4. So I have to subtract 4 to be fair. I can't just add 4 to the equation without taking it back away. So I've got minus 4, and the plus 5 was there to start with. So what is this? This is, I'll clean it up, x plus 2 squared plus 1. If you can write the expression as a square plus a constant that's positive, you cannot factor that unless you have complex numbers. This is a prime polynomial. We proved that last time looking at the discriminant. If you look back at the examples from last class, we showed that this was a prime polynomial. I have now derived that just by making these algebra steps. All right? Let's look at a different one. What if I had x squared plus 3x plus 2? Now we did this one last time, I think. I usually do this one. And of course, this is easy to factor, right? You just write, you guys can do it, right? This one? What is it? It's x plus 1 times what? x plus 2, right? But let me show you how it goes with the algorithm. So I take half of 3, which is what? 3 halves, yeah? You're like, oh, fractions. Yeah, I know, fractions. So plus 3 over 2. Now, to be fair, I have to subtract the square of this number, which is minus 9/4. 3 halves squared is 9/4. And then I have to add 2. All right, so let's clean that up. This is x plus 3 over 2 squared. How many quarters is 2? It's 8 quarters, right? So this is really minus 1/4. Now, most everyone in here should be using a calculator if you choose this path, right? To check on the fractions. Otherwise, bad things happen here, right? Now, a quarter is a half squared, right? So you, in your calculator, you take the square root of 1/4, you get a half. So this is a half squared. Now, what do I have? I have the difference of squares. So I can use the difference of squares formula, which I encouraged you guys all to, like, you know, put on your sheet of remembrance last class, right? It's the pattern. And so we just think of this as a squared, yeah, and the b squared. And so this gives me x plus 3 halves minus 1/2, parentheses, x plus 3 halves plus 1/2. Yep.
Do we have to use this algorithm?
Oh, no. No, certainly not. My point to you is there are ways of factoring quadratics without guessing. This is how. If you don't want to guess, if you don't like my guessing method, you could use this method. Now, it may be unfamiliar to you. I mean, it probably is. What's 3 halves minus a half? It's what? 1, right? And what's 3 halves plus a half? That's 4 halves, otherwise known as 2, right? So you're like, as you know, as I was advertising last time, math is not postmodern. There is, in fact, a right answer. There's not your truth and my truth. There's just the truth, right? I mean, there is some ambiguity. You could do x plus 2 times x plus 1. There's that freedom, but that's about it. Now, why don't we do it this way? Why didn't I start with this? It takes longer. It goes up our Achilles heel of fraction calculation, right? But on the flip side of things, it does allow a concrete method to solve any factoring problem. And this will also generalize to problems with, like, a coefficient which is not 1. So, like, for example, 5, if I was dealing with like this, ooh, I may regret that. let me do, I think we did this one last time, but I'll do it this time one more time here. I may regret this. I'll give it a try. So if we had 6x squared minus 23x plus 10. So we could use the method that Gabrielle was mentioning, and basically this kind of idea, right? You'd go through that. Here's how it looks with my algorithm, which you can not like or like if you want. I mean, now this is a little bit beyond the algorithm, see, because there's a 6 here. So in order to use my algorithm, first we have to get rid of the 6. How do we do that? How do you factor a 6 out of this? Six times what? Well, I'll do the easy part, x squared. What comes after that? Too close. What's that? Maybe 2? I was going to say minus 23 what? 6, yeah. Plus 10/6. And then I can apply the algorithm to this one because it's got x squared in the start. So I I take half of 23 over 6. What's that give me? 23 over 12. You square that. You subtract 23 over 12 squared. Oh, that's big. And then add 10/6 to it. I've gone this far, let me finish it. But I'm not so foolish as to finish it without a calculator this early in the morning. So 23 squared divided by 144, 12 squared is 144, gives me 529 over 144. And then I'll subtract 10/6 from that because well anyway. So I actually get minus 289 and I get 289. This thing here works out to 289 over 144. That is equal to, I think, 17 squared over 12 squared. Let me take the square root of this right quick. Square root of my answer. Yeah, 17 over 12 squared. So I would strongly advise if you go down this path using a calculator to do the fractions, yeah? And now I have the difference of squares, so I can factor it. So you guys have the benefit of being the last section of college algebra I'm teaching this material. I tried to do this yesterday evening. That's not quite right. Late afternoon yesterday, and when I copied the problem down, I changed one number, and then these horrible square roots appeared from nowhere. But so it's easy to make these problems worse. What's 23 minus 17? 23 plus 17. They're both minuses, right? So that's 40 over 12, right? Which is 10/3. What's 23 minus 17 is, 17 minus 23 is what? Minus 6, right? Minus 6/12 is minus a half. And so there you go. That's what it looks like factored. Now, if we went through like Gabrielle's method or the other method, what would the answer look like? It wouldn't look like this, right? You wouldn't have a 6 out here probably. You'd probably have multiplied that 6 through, right? You can split the 6 into a 3 and a 2. And if you do this as 3 times x minus 10 over 3, and then a 2 times x minus 1/2, we'll get the answer that you guys would get, which is 3x minus 10 times 2x minus 1. So if you go through your method, you should probably get this. So which is faster? It depends on what you know, right? If you know your method and you know it down, do it, fine. If you don't, and you don't want to learn it, you can use this method. Or you can use the guess and check thing like I did to start with, yeah? It doesn't really matter to me which method you use. You just need to find a method that works for you on each problem, yeah? So I should have a tutoring announcement up soon, and those folks can help you with the other methods that I don't tend to teach in here. Aw, man. Haha, I brought the juice. I think someone has, if they wash the board with water, it doesn't really erase afterwards. It's a problem, always a problem. Now, this algorithm I'm describing here in the middle board, by the way, this is what's known as completing the square. If you ever heard of that. We'll come back to this thing again when we talk about the quadratic formula, because that's actually essentially how we derive the quadratic formula. That same little bit of algebra. All right, so let me stop spinning our wheels on this issue. Let's go on here. So if you don't mind, I'm going to try not to talk about the algorithm again. for a while here until like a future class. And we're going to focus our attention on just the guess and check, all right? So example 6. Oh, man. Oh. So here's example 6. Here we have 12x cubed plus 10x squared minus 12x. All right. How do we factor this? So we look for a common factor. Thing that jumps out at me is I can pull a 2x out of all of these things, right? So 2x, that leaves me a 6x squared plus 5x minus 6. Now just check. When to check, I multiply these things back out, right? I get my 12x cubed, 2x times 5x is 10x squared, 2x times minus 6 is minus 12x. And then I got to factor this, all right? So I'm going to put a 2x here, I'm going to put a 3x there. I got to get a minus 6, right? So I either need, to get minus 6, I need either what? Like minus 6 is minus 2 times 3, or minus 1 times 6, or 2 times minus 3, or 6 times minus 1, right? I mean, those are, yep.
How do you know that it's a 3x on the parentheses?
It's a guess and check. So I could be wrong, yep.
Wouldn't it, like 3 times 2, that would be like your 6x squared, right?
The what?
Like your 3x and then times your 2x, that would give you that 6x.
Yes. Right, yeah, whatever I put there, when I multiply these two back out, I have to get back to that. That's right. So I'm going to try I'll try minus 3 and plus 2. Does that work? I don't know. Let's see. Does it work? I mean, definitely I have the minus 6, right? But let's check the middle term. So we have 3 times minus 3, which is minus 9x, right? 2 times 2 is 4. So we have minus 9 plus 4 minus 5. Oh, man. How do you fix that if you get minus what you want? Yeah? Just flip the plus and the minus and we'll be good to go. So we just go, aha. Well, we should have put a plus here and a minus there. And then one more time, we just think through multiplying it out, FOIL it out, right? 2x times 3x is 6x squared. 3 times minus 2 is minus 6. Then I need to check this times this and this times that, right? That gives me 9x minus 4x. 9 minus 4 is 5. We're good. So there you go. And you can't go further than that because we can't factor linear factors more, right? What's the only way you can really factor a linear factor? Did I show you guys this already? I don't know if I did. I can't remember. Did I do this one? Like 3x plus 8. Can you factor that? Pull the 3 out, right? Like this is pretty much all we can do with a linear factor is if we've got a leading coefficient of x, which is not 1, we can pull that number out. We just have to divide the other thing by that as well to be fair. Yeah. All right.
So you said you can't factor that out?
I can't factor.
Example 7?
Example 7, I would say that this is already in lowest terms.
Okay.
If the instructions said, please factor it such that the coefficient of x is 1. Factor it in terms of factors where the coefficient of x is 1. Then this is what I would have to do, because now the coefficient of x is 1.
Okay.
But, short of some really nitpicky instructions like that, I would just leave it as 3x plus 8 a lot of times. The advantage of this is if we go to the next step and ask, when is this 0? When is 3x plus 8 0? Well, I have to think about that for a second. When is 3 times x plus 8 thirds 0? Minus 8 thirds. It's manifest. It's clear from this expression that if we put in x equals to minus 8 thirds, this is 0. So that's the advantage of writing it this way, is it makes the zeros of the polynomial, like manifest, like just in your face right there. Not manifest in the sense of crystals and whatever that's all about. That's what I'm talking about. If you guys don't know what I'm talking about, that is better for you. Let's see here. So, let's see here. I may have done one of these last time. I'll do one again. Example 8. If we have x to the 4th minus 16, we do what? We do x squared squared minus 4 squared, and then this is what? It is the difference of squares, right? So how does that factor? So we have x squared minus 4, and then x squared plus 4. X squared plus 4, that's prime. We can't break that down further, all right? X squared minus 4, hey, that's the difference of squares again, right? That's x squared minus 2 squared. So this is x minus 2 times x plus 2 times x squared plus 4. And that's it. That's now it's factored.
Wait, so when you did the top half of the x squared double squared and minus the 4 squared, was that just like simplifying the x to the 4th and then minus 16?
Right, yeah. The thing is, I don't know how to factor a quartic right offhand, but I do know how to factor something that's quadratic, maybe. We have some tools for that. So if I can rewrite it as a quadratic in something, then I have a chance. Let me do this one's not in your homework, but it's the same idea. Like if I had x to the 4th plus 3x squared plus 2. This is like something we've already done today in last class also, but not with x squared. See, like, so if we look at this, this is x squared squared, right? Plus 3x squared plus 2. So if you want, we can make a substitution, right? We could let y equal to x squared. And then this would be y squared plus 3y plus 2. How do you factor y squared plus 3y plus 2? I would say guess and check, yeah? So 1 plus 2, we should be good. Right? So this is called making a substitution. Really, we're just trying to recognize the pattern. What usually happens for x is happening for x squared here. Yeah? And now we're not done, right? To finish the problem, we should go back to put y is x squared instead of y, right? So, and then, so like x squared plus 1 times x squared plus 2. Now, question. Are we done? Am I justified in underlining that and saying, hey, that's the answer? Like, can you break those down further? I've said no, right? If we have x squared plus something, that's a prime. Right? Now, if we have x squared plus 3x plus something, is that a prime? Well, no. I mean, it's a middle term that messes it up. But if it's just a square plus a number, which is positive, that's prime. All right, so I'll do one last example on factoring, and then I'm going to move on. So here I have a plus 4 to the 3rd power plus 729. I think this is kind of like one I did last time for you guys, but actually, did I do this one already? I think I did this one already in here, but I'll do it again. My apologies. So this is a cubed plus b cubed, where a and b are what? What was 729? What did we say? 729 was what? Cube, what cubed?
9.
Yeah, 9 cubed, that's right, 9 cubed. So this is b cubed, this is 9 cubed. And so we do the, this is a, how's it go? You guys gonna have to help me out here. I know there's an a squared and I know there's a b squared over here. I think it's plus b and minus ab. So you have the formula sheet, right? So you can check. Plus ba squared minus ab squared, b squared a. Yeah, okay. And then I put in what the a and the b are. We get a plus 4 plus 9. Yeah, I definitely feel like I did this already in here. I'm sorry, guys. I'm recycling here. I don't mean to do that to you guys. I'm going to stop here. We finished this last time, right? But you can clean that up. All right, let's talk about rational expressions. So I'll start out with something relatively benign. So you guys have to help me out. Have I talked about rational expressions in here already? Yes, no? Okay, good. Imagine you had 4 friends who all looked the same, right? And you had the same conversation with them on 2 different days of the week. Would you forget what you said to your friend? 1, 2, 3, or 4? I would. So this is what I'm battling in here. You guys are the 4th friend I've talked to. So you have to help me out here. Sometimes I lose track of, like, you know, what I've already said in here. So if I start like recycling something that I've already said, you guys got to like just stop me and say, hey, our time is valuable. Move on to the next thing. Yeah? Or if you're really lost on it and you just want to see me say it again, go for it, I guess. But here it is. So how do we simplify this rational expression and put it in those forms? So what you want to do is I just collect all the numbers, you know. So we've got 15 times 21 over 7 times 10. And then we have x to the 8th over x, right? Now, you could factor the numbers and cancel like factors, right? I'm just going to use my calculator at the moment. 15 times 21 is 315. 315 divided by 70 is 9/2. So the number in the front works out to 9/2. I'll use my calculator right now. And then what's x to the 8th over x? X to the 7th. Yeah, we have a winner. There you go. So that is the answer. Now you could also write this as 9 times x to the 7th over 2. Same answer. All right. How about this? What if I had x minus 3 over 3 minus x minus 3 over, I don't know, 4? How would you combine these fractions and simplify this? What could you do? I mean, what I would do, what's that? The greatest common denominator? We could do that, but let me be lazier. See, this one here, we have an x minus 3 on both, right? So we could just factor that out, and we'd have what, a third minus a fourth times x minus 3. Now we could do that greatest common denominator thing, and we'll do that in the next example. Okay, so, and a third minus a fourth, well, that's what? That's 4/12 minus 3/12, which is a 12th. Now, of course, you're like, well, what did you just do? Arithmetic. So if you're not comfortable with that, get out your calculator and try it. Yeah. So let's do something that requires common denominatoring. Is that a word? Maybe not. How about this? What if I had something like x over x minus 1 plus 3x over x squared minus 1. So I've gone from very elementary problems to this is a kind of moderately difficult problem, right? The way to think about this, right, is that x squared minus 1 is what? We factor that how? What I heard actually was just, but I believe in my heart you said this. Is that right? Okay, good. So if you look at that, what if you're adding like just, what if you add a tenth plus, 3, 50ths? Do you want to use 500th? Do you want to just multiply the denominators for your common denominator? No. You take the least common multiple, right? What's the least common multiple of 10 and 50? It's 50, right? So you just do like 5 plus 3 over 50. Basically I'm multiplying the first one by 5 over 5 and I'm leaving the second one alone. This one here, what's the least common multiple of x minus 1 and x minus 1 and x plus 1? Well, it's actually the second fraction. So like x squared minus 1 is what we'd like to have the common denominator. So I do x over x minus 1, right? And I multiply that by x plus 1 over x plus 1. That's something I can do without changing the expression. I can multiply by 1, right? We can add 0, we can multiply by 1. So what I'm saying is this is numerically the analog of what I just did up here. That's all. This is numerically like the same idea. Now the reason I did that is now we have a common denominator of x minus 1 times x plus 1, right? And once we have the same common denominator, then we can do what? Then we can add the fractions, right? Can you add a third to a fifth? What's 1/3 plus 1/5? You can't add those, right? But 5/15 and 3/15, you can add those. That's 8/15, right? You have to have the same denominator to add. So that's why we made a common denominator here. And then you just work it out. So this one would be x times x plus 1 plus 3x, all divided by x minus 1 times x plus 1. Now, matter of style, do you leave this factored? If you find a factorization, it's good to leave it factored because factoring it tells us things about it, okay? So this is upstairs, I've got x squared, looks like x squared plus 4x, right? I think we can do a little bit better. Can you guys tell me how I can make this expression a little bit, if I'm trying to simplify this, what should I do? I can factor what out? We haven't had one like this yet, have we? But this is oftentimes what you got to do, right? I heard an x. Yeah, just factor x out. So that's x plus 4. I've been focusing on the sort of more tricky factoring problems, haven't I? But there are also these basic easy ones. Not that this is an easy example, but this step going from here to here I would think is easy. And that is the answer. Now some of you are like, I thought we just cross-multiplied to add fractions, right? What would have happened if you used the cross-multiply idea in example 13? You would have ended up with a denominator which was cubic, because you would have multiplied x minus 1 times x squared minus 1, right? Which would have made the problem more complicated than it actually is. Because in order to get to that simplified answer, you would have had to take in that cubic, and you would have had to like cancel factors in the cubic with whatever you got in the upstairs thing. And it's better to do it with the least common multiple if you can think through it. Let me do another example here. What example am I on? 14? All right. about this? What if I have 3x, let me just say x, over x plus 2 minus 3 over x plus 1. Again, we want to add the fractions, add the rational expressions, and simplify. Okay, that's the instructions. By the way, leave yourself a little bit of room in these examples to write something else in once we get past this algebra part of it. I'm going to talk about domains in a couple minutes. What is it? No? What? It's not for me, right? The question? No, okay. I have to always ask, because sometimes there are voices in my head, and I have to make sure that, you know, it's not those voices, it's your voices. If it's your voices, it's okay. If it's voices in my head, then, I mean, it depends on what I'm telling myself, I guess. But how would you add these? Now these, look, genuinely x plus 2 and x plus 2 and x plus 1, are there any, like, common factors here? Well, yeah, they both have x, but that's not a factor, right? It's appearing additively. Like, I can't factor x out of those without making it ugly. I mean, I can factor x out if you want me to, but let's not do it. There, I factored x out. You don't want to do that, right? That's what I'm talking about, right? That's not. Is this allowed? This is not part of the, I mean, it is, but that's not what we're doing. So strike it from the record. And so this one, I think this one is one where we'll use just the cross multiply idea, right? So cross multiply is this pattern. If I have a over b plus c over d, we can just rewrite this as a times d plus b times c over bd. So you take this and you put it over there, right? And you take that and you put it over on the other side, right? Just like this. Really? Shush. That's odd. The area code is interesting. That's where my mom lives, but this isn't my mom's number, so. I don't really think there are many telemarketers in the mountains of North Carolina, so I'm like, what is that called? But anyway, x over x plus, so I should do what? I should do x times x plus 1. The minus, I keep the minus, right? Minus 3 times x plus 2 divided by x plus 2 times x plus 1. Can we simplify this? I think we can do a little bit more here, right? This is x squared plus x minus 3x minus 6. Be careful to distribute the minus, and you have to multiply it out, right? X plus 2, x plus 1. And so what's that upstairs? We've got x squared minus 2x minus 6 divided by x plus 2 times x plus 1. Now, sometimes the book is content with that as an answer. Like, it's like, okay, you're done, right? Other times, if the numerator is easy enough to factor, then go for it. You can factor it, right? Is that one easy to factor? I'm not sure. What do you guys, can we factor this x squared minus 2x minus 6? Does it factor nicely? How to get minus 6? Like, what, 3 and minus 2? Or minus 2 and 3? Those either give you a middle term of x or minus x, which is not what we have. The other way to get 6, minus 6 is 1 times 6. That will give you a middle term of either 5 or minus 5, which we don't have. This one does not factor nicely. You'll forgive me for doing the algorithm one more time today, but if I use the algorithm, this is x minus 1. You'll see why we couldn't do it. X minus 1 squared, and then I have to do minus 1 minus 6 is actually minus 7. So this actually factors to x minus 1 minus the square root of 7 times x minus 1 plus the square root of 7. So, I mean, does it factor over the real numbers? Sure. Does the book expect you to do this in section R4 or R5? No. This is not expected of you in this section, all right?
So you just leave it as that final
Yeah,
answer?
exactly. This right here is the answer for this Saturday's homework for sure. Now, by the time you leave the course, I would like you to understand that you can change this to that, but we're not quite there yet. We're going to spend like a whole day just on that, all right? Getting ahead of the story a little bit by writing that. Now, all right, so I have, at this point, we have example 14, and we have example 13. These are both nice rational expressions. I'm going to do one more here that's even easier to introduce the discussion. So suppose you have x minus 3 over x plus 4. We can ask the question, what's the domain of this rational expression? All right? So what's the domain of this rational expression? So we haven't talked about domain yet because the domain of polynomials is always just the whole real numbers. Because polynomials make sense whatever you do to them. Like you can plug in a negative number, you can plug in a positive number. They're either 0 or they're positive or they're negative. There's no division by 0 in the formula for a polynomial. But for a rational expression, if you have division by 0, we can't allow that, right? So the domain here would be x such that x is not equal to what? Fill in the blank for me. What is the one thing I can't allow here? Negative 4, right? Now, what about 3? What about 3? 3 makes x minus 3 0, right? Yeah.
It would be 0 in the numerator, so you wouldn't be dividing by it.
Right, he says it'd be 0 in the numerator, so you wouldn't be dividing by it. That's exactly it. Like 0 in the numerator, we don't care. Fine, no problem. 0 in the numerator just makes the fraction 0. Or later when we're talking about graphing, if you have 0 in the numerator and 0 in the denominator, that corresponds to what's called a hole in the graph. I'm jumping to the midway point of the course, okay? Anyway, so there you go. This is the domain. Now, this is what's called set builder notation, all right? The other notation here would be minus infinity to minus 4 unioned with minus 4 to infinity. Now, this is what's called interval notation. Now, I'm just mentioning that in passing here. Your homework does not require you to give the answer in interval notation. The homework expects the answer in like this kind of notation, all right? So, yeah. So let's go back to example 14 and example 15. Example 14 and 13. Why don't you guys tell me, what's the domain in example 13? I'll start us out. X such that x not equal to what? I heard a 1 and negative 1. What do you guys think? Do we have a winner? Are those the trouble spots here? 1 and negative 1? I think so. My curly brackets are not as curly as my curly brackets devolve the lower I get on the board, but so yeah, either one of these fractions, this fraction doesn't make sense when it's 1, right? This one doesn't make sense when it's 1 or minus 1. As you can see more explicitly from this, 1 and minus 1 are trouble. So you're like, well, but the first part makes sense at minus 1. It just doesn't make sense at 1. Well, when you're dealing with like rational expressions, you're only as strong as your weakest link. If any piece of it is not defined, it's not defined. All right? So that's the domain. How about this one? What's the domain in example 14? X not equal to what? What must we rule out in that example? I heard 2 and so we got votes for 2 and negative 1, or what is it? Oh, negative 2.
Wait, so what exactly are you looking for when you're trying to find the domain?
The domain is the set of x for which the formula makes sense.
Okay.
So we have to, we're trying to exclude the points where we get division by 0. And so far that's been relatively obvious, like from these formulas, what we're excluding. Let me make one that's a little bit less obvious. What if we had 3x over 3x minus 7? What's the domain of this? What is it that we're trying to avoid? We're trying to avoid 3x minus 7 being 0, right? So we put, if you want to, so I mean, sometimes I just write, I write an equality for what I don't want, right? So 3x minus 7 equals to 0. This is like, this is oops. If we have that, right? I mean, division by 0. So that would be 3x equals to 7. X equals to 7/3. So we want x not equal to 7/3. See, because this is the trouble. If we have that equal to 0, that's what gets us in trouble. Alrighty. Another simple polynomial arithmetic problem. If I have something like 15x squared plus 60x over 5x squared, how would you simplify that? So I'm going to write a few problems up on the board here, and then I'll work them one at a time. All right, so there's that one. Example 18 is going to be 18x to the 8th over 2x cubed divided by 81x over 6x cubed. And example 19 is going to be 8x minus 48 over 2x minus 16 divided by x squared minus 36 over x squared minus 4x minus 32. All right, so we're gonna chew on these three examples here. All right, so first things first here. Example 17, what can we do? We could factor out a 15x, right? So 15x, that leaves us with x plus 4 divided by 5x squared, right? So what's 15 over 5? 15 over 5 is 3, right? And what else can we do? What's x over x squared? 1 over x? Yeah. Sounds good. And I think that's pretty much it, right? So we've got 3 times x plus 4 over x. Now, your book sometimes likes this as 3x plus 12 over x. Honestly, I'll take either. Truth be told, I also like the following answer. This is 3x over x plus 12 over x, which is 3 plus 12 over x. That's also a perfectly good answer. There's a lot of, really, in my book, all three of these are like totally legit answers. So, but I think your book is looking for this middle one, what it's worth.